In this video lecture, we are going to discuss hyperfine structure and the quadrupole moment of linear molecules. Hyperfine splitting is a phenomenon that occurs when the interaction between the nucleus and the electron clouds of an atom, molecule, or ion causes small shifts in the electronic energy levels. This results in the splitting of the energy levels into smaller components called hyperfine structure. The magnetic moments of the nucleus and the electrons in atoms interact, causing the fine structure of spectral lines to split. Hyperfine structure is about 1000 times smaller than the fine structure. The splitting is determined by the quantum number of the nucleus. It is used in spectroscopy to determine the number and identity of nuclei and the distance of nucleus from the unpaired electron in a molecule. It is applied in radio astronomy, nuclear technology, and atomic clocks. Hyperfine splitting refers to small shifts and splitting in the energy levels of atoms, ions, or molecules. The interaction between the electron spin and the nuclear spin is known as hyperfine interaction, and the splitting occurs due to this interaction is called as hyperfine splitting. When the electron spin interacts with the nuclear spin, then each electron spin state splits into 2i plus 1 level, and it is known as hyperfine splitting. Here, I is known as nuclear spin quantum number. The rules to determine nuclear spin. A nucleus with an even number of proton and even number of neutron has zero spin. That is, the spin of the neutron I equals 0. For example, C12, O16, and goes on. When you are going to take C12, 6 protons and 6 neutrons are there. So even number of protons and even number of neutrons. Here I equals 0. A nucleus with an odd number of proton and odd number of neutron has an integral spin. For example, nitrogen 14. So 7 protons and 7 neutrons, where I equals 1. For B10, I equals 3. Boron 10. The nucleus with an odd mass has half integral spin. For example, hydrogen C13. So this will have neutron spin as 1 by 2. Beryllium 9, which will have the neutron spin as 3 by 2. So C13 is the isotope of carbon 12. So which is nothing but 6 plus 7. So odd number of neutrons. So which will have the neutron spin as 1 by 2. Here I is the nuclear spin quantum number. The nuclear spin can have several orientations. For example, when you take I equals 1. So this will have Mi, which is equal to plus 1, 0, and minus 1. So this will have a rule 2i plus 1. So when I equals 1 here, so this will become 3. So Mi will have 3 values, plus 1, 0, minus 1. Whereas I equals 1 by 2, this will have 2 multiplied by 1 by 2 plus 1. This will have 2 values. One is plus 1 by 2 and another one is minus 1 by 2. Suppose when you take I equals 7 by 2, then substitute here 2i plus 1. Instead of I, you just substitute 7 by 2. We'll have 8 values. So Mi goes from plus 7 by 2 to minus 7 by 2. For example, we will take a example as hydrogen. One unpaired electron. So here Ms equal to 1 by 2 of hydrogen interacts with its nuclear spin. So again I value will be for the nucleus I, the spin of the neutron will be 1 by 2. So therefore we'll have 2 values, Mi equals 1 by 2 and minus 1 by 2. Because 2i plus 1, you substitute I 1 by 2, so this will have 2 values. The energy of particular Ms state will be affected by nuclear spin, electron spin, interaction energy. So this is the splitting energy level of hydrogen atom, and this is about the first figure. In figure A, we could find out applying a magnetic field, and figure B shows the effect of nuclear spin on these levels. There are 4 possible energy levels of hydrogen atom are given by exactly like this. We'll find out now. So ms equals plus or minus 1 by 2. So when you are going to apply magnetic field, and this becomes ms will be plus 1 by 2 and ms will be minus 1 by 2. So one is spin up, another one is spin down. And when we interact with the nucleus, then we will have 2 more levels. For each level, we have 2 more levels according to this rule, 2i plus 1, which is equal to 2 multiplied by 1 by 2 plus 1, which is equal to 2 levels. So we have plus 1 by 2 will split into plus 1 by 2 and minus 1 by 2. Similarly, minus 1 by 2 will split into minus 1 by 2 and plus 1 by 2. Now, what are the applications? In radio astronomy, the heterodyne receivers are widely used in the detection of electromagnetic signals from celestial objects. The separation among various components of a hyperfine structure are usually small enough to fit into the receiver's infrared band. The atomic vapor laser isotope separation process uses the hyperfine splitting between optical transitions in uranium-235 and uranium-238 to selectively photoionize only the uranium-235 atoms and then separate the ionized particles from the non-ionized ones. The hyperfine structure transition can be used to make a microwave noise filter with very high stability, repeatability, and Q factor, which can thus be used as a basis for very precise atomic clocks. Now we'll look into the second title, which is nothing but quadrupole moment of a linear molecule. The quadrupole field is also a tensor of rank 2. This is the gradient of the gravitational field of the mass distribution at the origin of the axis of the system. Quadrupole splitting arises due to the electric field gradient. If the electric field gradient is equal to 0, then the quadrupole will be absent. If it is not equal to 0, it will be present. In the presence of asymmetric electronical environment, that is, asymmetric electric field gradient, the excited level splits into levels. It's a property associated with the shape of the nucleus. In certain cases, a nucleus may have a quadrupole moment. For a nucleus in a stationary state, the electric dipole moment is 0. It is due to its symmetry about the center of mass. But the symmetry need not be spherical, so there will be some deviation. The deviation of nucleus from spherical symmetry gives rise to electric quadrupole. Most nuclei will experience an ellipsoidal shape. This deviation from a spherical symmetry is expressed by a quantity called electric quadrupole moment. Electric quadrupole moment is denoted as Q, capital Q. It indicates the deviation of nuclear charge distribution from a spherical symmetry. Electric quadrupole moment is expressed as 1 by E times integration rho times 3z squared minus r squared d tau. Here, E is the charge of the electron, rho is the average nuclear charge density, d tau is the volume element, and r squared equal to x squared plus y squared plus z squared. And the first figure shows it's a spherical symmetry, so there is no quadrupole. Quadrupole moment is not there because it's spherical symmetry, so Q equals 0. But here, in oblique case, where A is greater than B, Q is negative value. That is, quadrupole moment is negative value. Whereas in prolate case, where B is greater than A, and quadrupole moment is positive value. Quadrupole splitting. Quadrupole's interaction refers to the interaction between charged particles in a nucleus which cause nuclear precession. Unlike magnetic interaction, the energy level of quadrupole interaction is not equally spaced, resulting in multiple precession frequencies. Electric quadrupole interaction describes the interaction of the nuclear quadrupole moment with the electric field gradient present in the place of the nucleus, coming from charge surrounding the nucleus with defined as the angle between the symmetry axis and the vector r, which is given as z equal to r cos theta. In atoms, hyperfine structure arises from the energy of the nuclear magnetic dipole moment interacting with the magnetic field generated by the electrons and the energy of the nuclear electric quadrupole moment in the electric field gradient due to the distribution of charge within the atoms. This phenomenon arises due to the interaction between electric quadrupole moment of nucleus and the electric field gradient. It occurs when nuclei having spin greater than 1. So this is very important. Spin is greater than 1 and it must have asymmetric charge distribution. And spin which is equal to 1, this will have symmetric, whereas the spin greater than 1 will show asymmetric charge distribution. The quadrupole splitting is not observed in symmetric cases for I equals 1. This produces an electric quadrupole moment. It happens due to inhomogeneous electric field. For an ideal cubic symmetry, the electric field gradient is 0. That is, there is no quadrupole splitting observed. The more asymmetric charge distribution, higher will be the electric field splitting and higher will be quadrupole splitting. Nuclei in states with an angular momentum quantum number I greater than 1 has a non-spherical charge distribution, which is nothing but asymmetric. This produces a nuclear quadrupole moment. The nuclear energy levels split in the presence of an asymmetrical electric field produced by an asymmetric electronic charge distribution. The charge distribution is called electric field gradient in the nucleus. All nuclei with a nuclear spin I is greater than 1, that is I equals 1, 2, 2, 3 or I equals 3 by 2, 5 by 2 have nuclear quadrupole moment, which is denoted as E capital Q. Here E is nothing but electronic charge. So I equals 1 shows the symmetric distribution, whereas I is greater than 1 shows asymmetric distribution. Q is the measure of a deviation of nuclear charge from spherical symmetry. The EQ interacts with the electric field gradient, which is equal to EQ star EQ, which is equal to E square capital Q multiplied by small q, which is nothing but nuclear quadrupole coupling constant. So nuclear quadrupole coupling constant is denoted as E square capital Q small q. This electric field gradient arises due to asymmetric electronic charge distribution. Quadrupole splitting. When a nucleus has a spin quantum number I greater than 1 has a quadrupole moment. In case coupling of nuclear spin angular momentum with rotational angular momentum causes splitting of the rotation energy level in a diatomic molecule. If the quantum number J of a rotational level is greater than I, 2I plus 1 level are produced. But if J is less than I, 2J plus 1 level results. This effect is one type of hyperfine splitting. For example, in HCN, you take N where I equals 1, all levels with J greater than 0 split into 3 levels. The energies of sublevel are proportional to the nuclear quadrupole moment and a function of capital F and J, where capital F goes from J plus 1 to mod J minus 1. Thus, the observation of nuclear quadrupole splitting permits the magnitude of nuclear quadrupole moment. This is an alternative method which can be used in nuclear quadrupole resonance spectroscopy. Quadrupole hyperfine interaction. The electric quadrupole interaction is the main cause of hyperfine structure, which is a splitting of rotational transition in molecules with nuclei having nuclear spin values I is greater than or equal to 1. The quadrupole coupling constant E squared capital Q, small q, is a quantity that can be determined by measuring the splitting. This interaction occurs when a nucleus has a non-spherical charge distribution and is surrounded by electrons with a non-cubic charge distribution. The interaction is a result of the electric field gradient at the nucleus. Quadrupole hyperfine interaction is a hyperfine interaction that occurs when a nucleus with a non-zero quadrupole moment interacts with a non-spherical distribution of electric charges. This interaction is described by the Hamiltonian, which depends on the nuclear quadrupole moment, the charge of the electron, and the nuclear spin. The nuclei with a spin I is greater than 1 lacks spherical symmetry along the spin and possesses an electric quadrupole moment EQ. Such nuclei are either elongated along the spin axis or shortened in that direction. One is oblate, another one is prolate. The nuclear moment EQ is a measure of the deviation from the sphericity, and quadrupole has units of centimeter power minus 2. Consider a nucleus and let V be the electric potential at its due to all electrons and the other nuclei. Then V is given as this equation 1.82 sigma over I E divided by Ri plus sigma over J Zj E divided by Rj. Here the summation is over all the electrons and J over all nuclei. I for electrons, J for nucleons. Small ri and capital Rj are the distances of the electrons and nuclei from the nucleus of interest. Zi is the charge of the jth nucleus. The electric field gradient, which is referred as E small q, along the Z molecular axis defined as equation 1.83. EQ equals d squared partial d squared V by dz squared, where the average is over the electronic states of the molecule. So here the expectation value, this is the average value. For a symmetric rotor, if the nucleus of interest lies on molecular symmetry axis, for example in CH3Cl chlorine atom, the first order perturbation theory gives the following correction to the rotation energy as EQ equals the first order correction E1 JKM, which is equal to this expression as given in equation 1.84. Here C equals F times F plus 1 minus I times I plus 1 minus J times J plus 1. F equals I plus J is a total angular momentum quantum number which takes the values I plus J to mod I minus J. I is the spin of the neutron, J is the total angular momentum of the electron. The quantity E squared Q, capital Q, small q is usually referred as a quadrupole coupling constant. When K is said to be 0 in equation 1.84, the result applies for a linear molecule. As example, a prolate symmetric rotor having a nucleus of spin I equals 3 by 2 on the molecular symmetry axis. For example, chlorine atom in CH3Cl. For J equals 0 and K equal to 0, F can have the value 3 by 2. For J equal to 1, K can have the values 0 plus or minus 1. And F will have 1 by 2, 3 by 2, 5 by 2. As we know, F equals I plus J. So F equals I plus J. Accordingly, we can obtain the F values here. The given possible values of J, K, F and the energy level based on the equation 1.84, the selection rules are given as del J equals plus or minus 1, del K equals 0 and del F equals 0 plus or minus 1, which allow 3 transitions. Without the quadrupole interaction, the J equals 0 to J equal to 1, the transition satisfying the condition del K equals 0 gives a line at 2B. So when J equals 0, K equal to 0, your EQ equal to 0 and F is nothing but 3 by 2. Whereas J equal to 1, K equal to 0, we have 3 split. So there will be 3 splitting. One is 1 by 2, 5 by 2, F equals 3 by 2. So there are 3 splittings. And what is the transition? The transition will follow accordingly this rule. Del F equals 0 plus or minus 1. So here 3 by 2, 1 by 2. The difference is 1. And here 3 by 2, so 5 by 2. Again the difference is 1. And 3 by 2, 3 by 2, the difference is 0. So we have plus or minus 1. Accordingly, according to this selection rule, it will follow. We'll have 3 transitions, 3 allowed transitions. First order correction to the rotational energy due to quadrupole hyperfine interaction is given as in the figure. And there are 3 rotational energies. EQ equals minus 0.25 E squared capital Q small q, and similarly minus 0.05 times E squared capital Q small q, and the another one at F equals 3 by 2 is EQ equals 0.20 E squared capital Q small q. With the quadrupole interaction, we'll have 3 lines of frequencies given by your nu1 equals 2b minus 0.25 E squared q, nu2 equals 2b minus 0.05 E squared capital Q small q, and nu3 is given as 2b plus 0.2 E squared capital Q small q. Here E squared capital Q small q is nothing but electric field gradient. Thus the frequencies depend on the field gradient along one principal axis. Transitions between higher base states are more complex and giving rise to more components. Their frequencies can also be obtained using the same equation, equation 1.84. The theory is much more complex for asymmetric top molecules, and the energy EQ generally depends on the field gradient along two principal axes.